¿Perdón? Hola, muy buenos días a todas y a todos los asistentes a esta importante sesión de nuestras tertulias. Para nosotros es un placer recibir hoy día la visita, la participación del profesor Thomas Nail de la Universidad de Denver. El profesor Thomas Nail tiene, bueno, una un prolífico trabajo en filosofía en este momento. Él comenzó haciendo su licenciatura en filosofía en la Universidad del Norte de Texas. Después se doctoró en la Universidad de Oregón y su tesis doctoral versó sobre el tema de la revolución política en la obra de los filósofos franceses Gilles Deleuze, Félix Guattari. Bueno, él fue entonces, en ese momento se interesó en el levantamiento zapatista en Chiapas, México. Esta investigación fue la base de su primer libro, Returning to Revolution, Deleuze, Guattari y el zapatismo, publicado en 2012. Hay que decir de que tiene una larga lista de libros, de textos, o sea, aquí resumo algunos. Está Returning to Revolution, Deleuze, Guattari and Zapatismo. Luego, The Figure of the Migrant, Theory of the Border, Lucretius, esa es una trilogía de Lucretius. Lucretius 1, 2 and 3. Luego, Being and Motion, Theory of the Image, Marx in Motion, Theory of the Earth, and the Theory of the Object. Aparte de eso, comentábamos antes de comenzar esta sesión acerca de otros escritos relacionados con Theory of the Earth que tocan el problema, bueno, del daño que estamos haciéndole al planeta. Está entonces, hay un texto de él que es sobre el biopower. Bueno, lo que ha estado haciendo Thomas durante todo este tiempo, o sea, el nudo central, el eje central de su filosofía es la filosofía del movimiento. Estudia los patrones de movimiento y a medida que fluyen y se entrecruzan. Entonces, bueno, no quiero ahondar más en esto porque es realmente un apasionante estudio que parte del movimiento y cómo estos patrones van construyendo los objetos. Y con esto quiero dejar entonces al profesor Thomas Nail, agradeciéndole nuevamente que se conecte con nosotros y que participe en esta tertulia filosófica sobre fundamentos de las ciencias. Gracias.
Thanks, Rolando. Thank you so much for inviting me to participate in the group, and thanks for everybody in the group for attending, and everybody on YouTube for watching. Yeah, so it's an interesting audience, and I've written a lot of different things, so I'm happy to talk about whatever folks want to talk about, but probably the best way to start is just kind of introducing myself a little bit, where I'm coming from, how I started doing this stuff, and then just kind of a general introduction about the project, what I wanted to do with it, and then maybe I'll say a few more specific things about the theory of the object, the book that tries to sort of, there's different pieces of it, but it's partly a history of sciences, mathematics, logic, and technology. And it's in part, it's a philosophical project as well to understand what it is that the sciences historically in the West are engaged in when they're doing science and talking about objects. Okay, so I'll start just by saying, how I came to this. So in my last year of graduate school, I applied for a scholarship, a Fulbright scholarship, and I went to go work with a migrant justice group known as Illegal in Canada. So I spent a year just working with No One Is Illegal. And if you haven't heard of No One Is Illegal, they have it's a pretty large global group. They have organizations in a bunch of different countries, certainly not all of them. But they're more on the radical side of migrant justice, calling for for universal status for everyone. And this really appealed to me. And I was writing my dissertation and project thinking about Zapatismo, thinking about global migration, working in political theory in an area where there really wasn't at the time a lot of political theory about migration. When you read a fair bit of political theory, especially in the liberal tradition, you get a lot of political theorists who are like, this is not really a problem, to like a serious one. It's a minor thing that's like, it's a small problem within a larger context. And I mean, that's like pre-2010. There's not a very large literature on that. Since the European migration crisis, since increases in migration related to climate change, there's been more philosophers engaging with these questions. But at the time, it was something that I was really thinking was not just a side issue in political philosophy. This is actually, for me, a central aspect of political theory. And I wanted to rethink all of political theory from the perspective of migration. And that second book on borders was also thinking about borders, sort of flipping the script of political history and thinking about borders as constitutive of states, the ways in which bordering techniques make it possible for societies to stabilize, the ways in which migration and migrants through world history, not just Western or 19th century, I mean, since the very beginnings, have been that migrants are constitutive of societies and stabilize them as metastable states. That was the beginning of the project, and I was thinking about those things. And as I was researching stuff on migration, I was thinking a lot about movement, and I was looking at it historically. But at the same time, I was reading, philosophers alongside these historical names for migration. And one of those was in ancient Greece, the barbarian. And one of those philosophers, of course, was Aristotle, who theorizes the barbarian and says, it's interesting the way Aristotle, to me at the moment, it was very interesting how Aristotle's description of the cosmos as this sphere, where there's this center and everything rotates around it. And then what he was saying about barbarians. And one of the things Aristotle says is, well, barbarians aren't political because they're always moving around. It's partly their mobility that they don't stay in the same place that makes them fundamentally apolitical. Also, they don't speak Greek. Also, they don't have the polis. They aren't Greeks with the city and the logos, and that makes them barbarians. And to me, the fact that he thought about movement as this kind of inferior feature, and again, the ultimate goal here for Aristotle was to describe a universe that was in some ways ordered, that had a telos, it's got a goal, and it's got an unmoved mover at the center of it. The unmoved mover moves everything, but himself doesn't move. And this image of a universe tied to immobility really struck me as connected with the historical colonization and militarization and empire of the Greek city-states and their institutions of slavery that made it possible for Aristotle to sit around and think about philosophy. In fact, the very beginnings of philosophy are founded on institutional slavery and the kidnapping of so-called barbarians, just basically non-Greeks around the Mediterranean. In any case, seeing the immediate connection, it kind of drew me to see the connections between the politics of migration and the ontologies of just the ontological relationship to motion. And in short, it wasn't just Aristotle. Archimedes, Newton's clockwork, clockmaker God, and Descartes' clockmaker God, and even Einstein's block universe. There's this way in which the sciences and philosophers themselves in the Western tradition have been sort of obsessed with explaining why things move, which is to say, explaining motion by something else that doesn't move, something that's static, something that's immobile, whether those are universal laws, whether they're eternal gods, unchanging forms, whatever that's going to be. And so my works have tried to track down the history of those terms and how they account and explain motion. Almost no one is willing to accept that things move without cause, without higher explanation, that everything is in motion and that there is nothing in the universe that doesn't move. And that is most of what, in my opinion, in my research, that the history of Western thinking has tried to show. And I don't think they've succeeded. And I think Einstein was the last holdout prior to quantum mechanics, where we now, I mean, at this level of experimental science, we don't know of anything in the universe that doesn't move. Everything moves. This is where we're at. And I'm not saying this couldn't change. Maybe we'll find something, but for the moment, and so maybe I'm wrong about this orientation historically, but at the moment I'm right. And this is where we're at. Everything is in movement. So if that's true, what exactly have we been doing, in the Western tradition, thinking about trying to explain movement away by gods and forms and clockworks and block universes? What have we really been up to? If we've never been talking about stasis, what have we really been up to? And I mean this not just in, each of the books that I've written has tried to kind of track a different historical trajectory. The arts, so architecture, all of the arts, literature, the beginnings of the novel, paintings, thinking about the way that art has grappled with this problem in the Western tradition, thinking about the way that the sciences have grappled with this problem, the way that philosophers have grappled with it, and the way that politics has grappled with it. That was several of those core books on aesthetics, science, and politics, to think about how movement has been, people in the West have tried to explain it. And also, importantly, the ways in which the things that have moved have always eluded or escaped the grasp of those methods and those ways of doing things. Sometimes in productive ways, sometimes in destructive ways. And that's part of those books as well. The last book in that series, The Theory of the Earth, was to look at the question of movement at a really large level, not just at the scale of like human intellectual history in the West, but actually cosmic history, terrestrial history, the history of the cosmos, how it's unfolded, and all of its movements, how motion and patterns of motion have shaped the evolution of the planet, the origins of life, the beginnings of consciousness. The book on consciousness is not done yet, but it's in the works. Anyway, so basically kind of rethinking the entire history of thought from the perspective of movement, assuming, as we know now, that everything is in movement. What have we been doing, and how has that unfolded historically? Okay, so that's like, it set me down, like this project at Migration set me down all these other paths of thinking about movement in all these different registers that were connected with the political events. And that ended up, taking a lot of years to write all those books and thinking about all those things, which I'm still very much in the process of thinking through, and would love to hear some of your, sort of disciplinary thoughts of how movement figures in our disciplines. But before so anyway, that's the general framework. I will say the other thing I want to say about the general framework is there was, what was the goal? Like, what was the product of all of that work? It wasn't just to track history. It was also a philosophical project. And I'm making a very large synthesis here now to say what I think some of the most generalizable outcomes were from all of those books. And if I had to kind of narrow it down, I would say there's really three concepts that came out of that work. The goal of which was to understand, to kind of use it as a theoretical framework. Three concepts to understand reality, essentially, across every scale, from the cosmos all the way down to subatomic particles and, quantum fluctuations. how to think about, so this is like obviously across disciplines, but also just across scales of reality and traditions. It wasn't just a political project, not just a scientific project, but a way of using these concepts to reinterpret and think about all of them as patterns of motion. And I'll talk about those three concepts in a minute, but I'll just say them now and then I'll define them more precisely in a second. Flow, fold, and field. These are the three ideas that I want to talk about today. Specifically, I'll talk about them with respect to the definition of an object. But to me, these are three concepts that have functional, usable outcomes for rethinking every area at every scale. So they're philosophical concepts. You might feel like, well, they're very general. How do they work here? Yes, they're very general concepts. They're meant to be applied in specific areas, but they're supposed to work across
Please,
every scale.
Can you repeat the concepts? Flow,
fold, like fold, like pleat, and field.
Field, like a field.
Field.
Okay, thank you.
Yeah, like a field. Yeah.
Thank you.
Yeah, thanks. Yeah, so those are the three concepts that I think that I show in all the books that are kind of at work in all these areas across scales and across history. And then there's 4 patterns of motion. So I don't think it's excessive, you know. Some philosophers have a million concepts. I've really tried to pare it down to just these 3 plus these 4 patterns of motion. So if everything is moving, it's not like it's just moving and that's the observation. That's not very helpful theoretically to just say everything's moving. I mean, everything is moving, but that doesn't really help us think or solve any problems. What does help us think about both historically how these patterns unfold is to have some patterns. And now I'm going to go through them. I'm just going to say them now, and then we'll then talk about them. Actually, maybe now is the time to talk about these patterns. But across the areas in aesthetics and politics and science, there are these 4 patterns of motion. And the first one, maybe I should share my screen here, a whiteboard, so I can draw. Okay, hold on just a second. I clicked the wrong button.
Rolando, you should share the. Yes, sorry.
Okay, I have a whiteboard here. So the first pattern of motion, again, I'm thinking about everything here, groups of migrants, but also, you know, molecules, and also, you know, works of art and traditions of ways of making art, is centripetal. So centripetal, hold on a second here. I mean, you probably know what centripetal motion is, but I'm just going to draw this. It's a movement from the periphery to, it doesn't have to be a single central point, but some kind of central region. So the way that things move from the outside, from the periphery, toward a center. So each of these patterns is my argument, and I can't possibly summarize the whole thing. So sorry if this sounds very general. All I can say is I have written books trying to show all of how this is true. Right now, I'm just going to say it and try to give some little bits of evidence and to give you some sense of what I'm thinking here. These 4 historical patterns, so the other one is centripetal. Sorry, let me just say what they are first, and then I'll give some examples. The second pattern is, sorry, I don't have a fancy pen. Rolando has such a nice pen and whiteboard, and I'm just drawing with my mouse, okay? So you gotta give me a break on my drawings here. Is centrifugal. So from a central region outward. The next one is what I call tensional, and that is where you have sort of linked, kind of rigidly linked pieces. So I mean, I wish I could animate this to show you, but imagine that each of these is like an elbow joint, right? And a forearm. You can move these, but they're all linked together. So if we moved one of these pieces, it would move the others, but always in a kind of rigid, linked way. And so I call this tensional motion, just meaning that things are kind of locked in a tension. They're together, they move together, but it's precisely they're being separate from one another, held apart and held together. If that makes sense. We can, if you have questions, let me know here. But the other one is elastic movement. And the way that I think about elastic movement is, yes, very much like a rubber band. It can be stretched. There is a point at which it will break, but it could be stretched a certain amount before it will contract again. So it's defined, the movement is defined by expansions and contractions, and most importantly, flexibility. It can be bent and moved around. It has a range of possible activity. Okay, now I'm just going to give some examples of these, I'll pick a domain, but we can talk about other domains. If you think about, one way to think about human history, again, it's not to capture every single way human societies and civilization is moved. One of the projects in the beginning is to kind of gather things together from the periphery. So you can think here about prehistory, Paleolithic period, where humans are first gathering together, again, not cities yet, but they're gathering the periphery and bringing it to a fire, some central region, some encampment. They're hunting, gathering, bringing it back to the center and establishing regular groups of people together in places. Obviously that increases with the Neolithic, but from the transition from the Neolithic to city-states, once you've accumulated a center, right? Once you've hunted and gathered and developed agricultural surplus, you start gathering it and storing it in grain silos, and it becomes possible. Again, this is not an evolutionary necessity. It becomes possible for people to begin to develop things like cities, early cities that are based on these accumulations. And once you have accumulations of materials in a city, it's possible for somebody, right? Kings, emperors, despots, and so on, to then wield that, to consolidate that power, hold it against other people, to control the means of life and death through controlling agricultural surplus, and begin to have laws. We can also think historically about the origins of math and science here with scales of measurement in ancient Sumer. The invention of a whole system of weights and measures makes it possible. It's invented by a class of priests, and then it's imposed upon the periphery, which is to say the city moves outward in all directions to the periphery, kidnaps people from the periphery, enslaves them and uses them to build a military, uses systems of weights and measures to begin the starting points of economics, of systems of debt and credit, money, and the beginning of money. Tensional movements. Here we're skipping ahead here past the world of ancient empires to the world, at least in the case of the European tradition, to feudal structures, which is to say groups of interlinked but non-centralized authority. So these are, groups. Feudalism is a really great example, or structures that are like that, where they're tied together by juridical or legal structures. They have contracts of agreement, systems of vassalage, meaning that, there's one person who then grants a piece of land and authority to somebody, and in that area they remain, the feudal lord remains autonomous and powerful, but they're connected by legal structures. And so it's not necessarily even territory that's important as it is in centralized empires. It's actually legal code. So the law follows people where they go. Wherever you go, you're always a serf of some particular lord, and subject to taxation and all that stuff. Elasticity. And so we can also think here about, gosh, I don't want to go too deep into the technical details, but for me, this is the very beginnings of thinking about, in science and mathematics, thinking about, I'm thinking about Orem, Nicole Orem, and the beginnings of calculus, where you're dealing with not just quantities, you're dealing with changing quantities. That's the beginnings of the problem of calculus, is thinking about how it is that quantities can change and fluctuate over time. And what you're trying to do is coordinate two different degrees in in a diagram where there's an XY axis, you get the coordinates, the invention of the coordinate system. Descartes wasn't the inventor of that. Nicolas Rem really was, that's the beginnings of this whole idea of intensive and extensive changes that Descartes picks up on, and other later, theorists, Leibniz and Newton, end up developing into calculus. But the basis of it is that you've got an XY axis that's intension, which is to say there's a coordinate of two different axes. Whereas in ancient mathematics, you're often and sciences, you're dealing with pure quantities. And there's questions about qualities and qualities that are irreducible to quantity, like speed. And that's what starts, the beginning of the calculus, is thinking about velocity as something that the ancients never thought you could quantify. Color, speed, these weren't technically areas of scientific quantification in the ancient world, and nobody thought about them in that way. But over the medieval period, increasingly, people can start thinking about those things. But what you're doing essentially to measure velocity of an object, you create an XY axis in which you measure velocity and position, and then you alternate those things. Sorry, you see how this could really go down a lot of paths. I'm moving quickly here, but just trying to give some examples. The final one is elasticity, and I'll just give an example from basically statistical mechanics. This is like a modern, so the time periods here are, the first one is largely prehistory. We're talking about a really large period of time in which this pattern prevails. It's not the only one. I'm not saying it's the only pattern, but it is a really dominant pattern that structures most of life. And the centrifugal one is part of the ancient world. The tensional one is part of the medieval world. Again, I admit that this framework and my research is limited just geographically of the area that I've studied so far. The other one is modern. So when I say medieval to early modern, I should say. And then this last one, elastic, is modern period. So we're talking about kind of modern statistical mechanics. The shift that happens from kind of more classical to statistical mechanics is that you're no longer, you're dealing with like ranges of possibility. What is an object? It's a range of possibility. When you have, so just one example of one of there's a million different theories in statistical mechanics. We're talking about chemistry, we talk about physics, we could talk about all kinds of things, but again, I'll just give one that might help characterize this. Einstein's theory of relativity. That is a way to think about, again, we could talk about fields in mathematics, we talk about group theory, but in Einstein's theory, we're talking, the way that he thinks about space-time itself is like a fabric. It's a stretchable, elastic fabric. It's a range of possible positions that anytime we look at it, all of these ranges of possible positions are relative to one another on that field. So what is an object? Well, an object depends on the distribution and relative ranges of possibility in that field. So again, we could think about probability. Just the invention of probability theory. It's a modern kind of, in my phrasing of motion, it's an elastic one. Anyway, I'm feeling now that these arguments might not be my evidence might not be very convincing to you, because it really takes quite a bit of detail to show how each one of these things fits into this pattern of motion. Or in other words, when scientists, philosophers, and artists describe what they're doing, they often use very kinetic language to talk about these patterns. You might think, well, this has nothing to do with motion. You're projecting these patterns of motion onto these traditions. My point would be, again, that nothing is static. If nothing is static, everything is in motion. What humans are doing when they're doing mathematics or they're doing science is that they're moving in various patterns. They are describing the world according to patterns of motion, even if they don't think that's what they're doing. So part of what I'm trying to show is that despite the discourse, philosophical and scientific, about trying to find static structures and about that being what it is, it's not actually about that. It's actually about these patterns of motion that are really at work underneath that then get described in other terms, largely abstract. Okay, sorry if that's too much into those patterns of motion. Let's talk about, let's move to the theory of the object. And just let me frame the problem this way. I mean, there's a million ways we could talk about theories of the object and ways to frame it, but I'll just give you my own here. What is an object? That's the question of that book. I've thought about it in terms that the sciences historically in the West have kind of made this domain, like what objects are, their domain of study. Again, not that that's exclusively what they do, but it's often what they are characterized by, is the study of objects, which is to say entities that are relatively discrete and measurable by some standard of measure. They are making a measurement. They are trying to determine some kind of unity. If that's not what they're doing, then I think it really undermines pretty much every study if they're not really dealing with determinate units. Now, but what determinate and what a unit is, of course, is historically variable. So let me give you start with two very old ideas of what an object is. One of those is Platonic. I mean, they're old ideas, but they're also very contemporary insofar as many people believe them spontaneously. One is the kind of Platonic view that what is an object? What is a number? One, for instance, does one exist outside of space and time, whether there are humans or not? Some mathematicians will say this very clearly, that, you know, the unit, one, whatever, or the form, it's just real. Mathematics is real, whether you like it or not, whether there are any humans or not. There are really, there is a system of numbers. For Plato, these are the, you know, unchanging forms. They exist outside of space and time. Some mathematicians, when asked, will say, yes, that's what we're dealing with. We're dealing with form, pure form outside of space and time. So that's one theory. Again, sometimes just spontaneous in mathematicians that will have this Platonic view. The second one, in theories of objects, but also of mathematics and science, is kind of more Kantian. Again, you don't have to have read Kant to come to this conclusion, but people might say, and do say, that objects, and when humans do science, what they're doing is it's totally subjective. It's human constructions. Humans are making up this thing called numbers, and then they project it onto the world, and it's very useful for them. It's very functional. It's a utilitarian approach. It's instrumental, if you will. That humans, based on whatever, I mean, you could say it's based on their brain. You could say it's based on, for Kant, ideal structures of consciousness, whatever you want to say, or you could even say it's social. You could have a kind of social instrumentalist idea of science. Science is there to make things easier for us to accomplish certain goals in an effective way. It doesn't necessarily have to do anything with what's really out there in reality, but it's constructed inside of our mind. Okay, so in both of these stories, so I'll say just a couple problems with both of these ideas about what an object is and therefore what science and mathematics are trying to do. Both of the theories are based on stasis. They assume something static at the foundations of what math and science do. The first one, for Plato, what's static are the forms themselves, right? The pure unchanging forms outside of space and time. That is a key feature. They don't change. Math isn't going to like suddenly become totally different than it was before. You're not going to have that problem with this idea. We might not be able to get to it, but there is a fundamental unchanging nature of the universe that we are getting closer to or trying to get closer to. So it's static, the Platonic view. The Kantian view is similarly static, except it's not the world that's static. It's the forms inside of our brain that are static. Those are fixed. Those are unchanging. We're never going to get outside of our own heads because the brain or the human mind is structured in such a way that it's going to find these forms every time, everywhere. And so the consistency is based only on the consistency of our own structures and not the world. Okay, so again, it's based on stasis. For similar reasons, both of these ideas are also ahistorical. The Platonic one, that one's obviously ahistorical. It's got nothing to do with history. Whatever happens in the historical material world has nothing to do with the forms in themselves. The Kantian one, there might be some changes to the way that humans go about exercising them, but ultimately the conditions for math and science are inside of us, and those insides are unchanging. It's the same biology, it's the same mental structures, it's ahistorical, and it's static in both those accounts. Now, there are two alternatives to these in contemporary philosophy. One of those is the relational theory of objects. We could cite like different people that have put this forward. I'm just going to cite here Bruno Latour and actor network theory. For Latour, you're not dealing with what an object is completely reducible to the relations, the relational network. An object is just a node or a terminal in a network of relations. Now, you might say, well, this avoids the Kantian and the Platonic view by saying there's just relationality, and objects that we measure or make discrete or whatever are just nodes in that. But there is a problem, and that problem is, well, if it's just this network, and for Latour, it's very much a determinate network, okay? That's the key word here. It's a determinate network of determinate relations. The question is, why would those relations ever change? What is the source of agency of change? And this is the question asked by Graham Harman, and this is the other theory that's an alternative to the first two, called object-oriented ontology. And the idea of object-oriented ontology, at least on this point, is that you are dealing with relations between objects, but you are always, in every case, you have objects that are irreducible to the relations. Okay, that's the key difference, is the objects are irreducible to the relations, meaning that there is something in the object which is the source of change, and it is not a relation. So for Latour, it's all relations, and for Harman, there's just objects, and they do have relations, but there's something that can't be captured. In fact, it's kind of mystical, but Harman says that it's absolutely the object's essence withdraws. It has a kind of, he says, like volcanic energy. It has a hidden power. It has a kind of agency. But he also says that the objects, now this is where it gets a little bit Platonic sounding, that the withdrawn essence of the object is it transcends the world. It's not part of the world, and it never interacts with the world. Now, you might be wondering, well, if it doesn't interact with the world, how is it changing anything at all? And the answer, I mean, he just says it is. My opinion is, how could it possibly do that? It doesn't make any sense to me. And he's very explicit. You can, so in my book, Theory of the Object, it's just in the introduction where these are all cited. But he just says that it does. But to me, I don't think it can. It's pretty abstract. Now, let's talk about flows. This is my theory of the object. Sorry it took us so long to get here. I am wrapping up very shortly. Like, give me 5 minutes. And then we can discuss about whatever you want. But these are the concepts. This is the alternative theory of the object that I would propose, that would be able to think the agency of objects and relations without these problems of stasis or a kind of ahistorical orientation. We can really think about the history, a real history of objects, in which objects really change what they are, and we as ourselves objects in that world think about how those things change. Okay, so the first idea is flow. I represent it just by an arrow. I hope that's not too abstract, but I'll say what that is. The flow, when one way of where to start here. The idea of flow is based on the just kind of historical experimental idea in quantum physics that there's nothing in the universe all the way down, all the way up, that's totally static. So the flow is just meant to characterize movement first and foremost. If we're going to start to think about anything, we should start to think about it from what's going on, which is that it's moving, not from stasis. The second feature that I would want to say about flows is that they are indeterminate, meaning that they are not determinate, like Bruno Latour, or you're not dealing with determinate things. And this is another key word that I don't have time to talk in detail about the tradition of process philosophy, but that is a tradition that in philosophy that I'm from, that I think through. And flows are a way to think about process. I'm not the first person to talk about flows, obviously, but I do like the word. I think the people who use it get a lot out of it, and I'd like to keep going with that. It's a process, but it is importantly an indeterminate process. I mean, I would say that all processes are fundamentally indeterminate. That means it's not one state or another. We're not talking about a being. We're not talking about a non-being. We're talking about a becoming, a process. And that's the starting point for thinking about anything, at least in the way that I think about it. The second term is that the idea is that these flows, movements at every scale are happening, and that these movements also, they swerve, right? I mean, like Lucretius says, they move around unpredictably. That's part of the indeterminacy. And when they move around, they intersect. Here, it's kind of abstract, but it's not a perfect circle. Rolando says that the best image is like a helix, like a double helix, and that's great. Like, I like that idea too. So here, that's consistent with what I'm drawing here, because it's looping constantly. So you imagine that the flow of energy in the cosmos at every scale, we're talking about the movement of energy in the cosmos through the Earth. It cycles through the Earth, and then eventually the Earth breaks it down, recycles it many times, breaking energy down, and then releases it into space. As the planet goes forward through history and eventually dissolves or is sucked into a black hole. You're dealing with cycles of energy. So the flow, and this is what I call a fold. Again, the terms we could, there might be other terms that other people have used. I like the word fold. Again, I'm not the first person to use this. Deleuze uses this, Lucretius uses this. Lots of people use this idea of the fold, but there's something about the cycling of energy. Now, the cycling of energy is always a cycling, right? The process never stops. What you are not dealing with, and this is what I would contrast the idea of the fold with, is just a completely enclosed, discrete unity. There are no unities in the universe. There are no discrete unities. There's nothing that's enclosed in itself, cut off from the world. I mean, that is, by the way, that is the definition of objects that Graham Harman uses, is he says they are vacuum sealed. My view is that they are not vacuum sealed. Nothing is vacuum sealed. Objects are metastable. So the fold is meant to capture this idea of metastability. Like a river flows and eddies in a spiral, this is the eddy. And every eddy is also simultaneously, it's got entropy. It's releasing energy at the same time. So it's cycling energy and it's releasing energy. Okay, third, and by the way, this circle part, this is the object. This is what I call an object, is the cycling of that metastable state. So objects are all metastable, and we can think about these across scales and domains of knowledge. But when you think about objects, first of all, it's kind of abstract to just think about objects, because why? Flows are constantly iterating and metastable. They're always cycling through. You're always dealing with qualities, what we call qualities. None of these things are separate from one another. But where things touch, where things intersect, we get qualities. So this process of cycling is objects and what we call quantities, units of measure. The qualities they don't necessarily have a quantity. You can look at anything from a purely qualitative perspective. You could talk about temperature as more or less, or you could say it just feels this way. We could talk about singular qualities. So qualities and quantities are two aspects of the same thing. There's never a quality without a quantity, never a quantity without a quality. The two go together just in the world, in nature. But we can, if we want to, just look at the quantitative objective aspect, or just look at the qualitative aspect. And those are typically what's called science and art. Art supposedly is dealing with qualities, science with quantities. Okay, final concept, and then we can discuss and yeah. Sorry if it's a lot. Here's the loops, Rolando. One way to think, like, this is what's going on. You have, because you never just have one fold, you always have a lot. Energy is flowing through many different stages. It's iterating. One loop breaks it down. That energy is taken up by another loop, and that cycle, that series of objects can be repeated. So a flow of energy moves through. So this is a very materialist kind of project, if that's not obvious already. Like I am a materialist of sorts, a process materialist. Like I don't think that there's anything called substance, but I do believe that we are dealing with something that historically we can call energy or matter. It's flowing through each object, and then after it passes through each stage, the whole process can begin again. So although this sounds, and then of course at every stage also energy is leaking out. So we could even take things that look very static to us. A chair. A chair looks like it's just sitting there, but a chair is filled with all kinds of objects. There are all kinds of loops. Energy is coming into that chair. It is vibrating back and forth. The molecules of the chair are vibrating back and forth. Each of those vibrations is what I'm calling an object. The molecules, the atoms inside are vibrating at a frequency, at a specific frequency. Not randomly, but at a specific frequency, and that frequency is the oscillation of these loops that I'm trying to describe. But at each oscillation, you're always losing energy to some degree, and that lost energy is back into the system. To the degree to which all of those objects hold together, vibrating back and forth together, then we call it an object. We say, oh, look, there's a chair. But the chair is just energy that is vibrating back and forth within a certain range. And this is what I call a field. So there's more technical terms, there's lots of vocabulary. I think this already might, maybe I've given too much. But these are the three ideas: flows, folds, and fields. And it's important that the folds and the fields, they're all made out of flows that are indeterminate, but they're indeterminate processes that have formed metastable relations in a network, and that's what I call a field. Okay, I think I'm at time here, so I'm going to stop just to hear what you all have to say, and we can go from here. So thanks for your patience. Yeah.
Thank you, Thomas. So, yes, Juan.
Yes, thank you very much. I like a lot your presentation. I'm trying to understand. I have a little question about these three notions of flow, fold, and field concerning the patterns of motion. No, you describe. My question is about the notion of prediction, because you say, okay, flow concern process, and process is undeterminate, and I wonder what is the place for prediction? Is it prediction possible or not? What is the range of this pattern you describe? Yes, is that?
Yeah, no, that's great. That's a great question. So here's what I'd say about prediction. The first thing is that ultimate prediction is not possible because of quantum indeterminacy. Now, I'm not saying there aren't quantum theorists out there trying to really solve this problem and come up with a theoretical framework in which, oh, actually, like David Bohm or something, like, oh, actually the universe, there's a global deterministic equation for quantum mechanics, and that Schrodinger's wave equation is actually a description of the universe, and it's really out there, but locally it looks like it's unpredictable, but really it's deterministic. Now, there's lots of interpretations of this. My position is that we should just look at the experiments. So I don't have a theory so much about it as just let's sit with where we're at right now. And where we're at right now is that we cannot currently predict with any absolute determinacy the velocity and position of an electron. We can't do it. And it looks like that's fundamental. Now, could I be wrong? Definitely. Maybe I'm wrong about this, but so far nobody's been able to disprove this indeterminacy. There is a fundamental indeterminacy between position and momentum, Heisenberg's uncertainty, whatever you want to call it here, that makes it impossible to get fundamental prediction. Now, that doesn't solve the problem because we still want to make, okay, fine, but it's pretty accurate. Quantum mechanics, the equations are still pretty accurate in terms of prediction, partly because the way they do the measurements, but let's bracket the measurement problem here for just a second and say, fine, you get some predictions, but here's what I'm interested in those predictions from a philosophical perspective. Those predictions have their limit, at the 13th decimal point, they've got a limit. There's a point at which they just can't. So yeah, you can get predictions based on, you could just be Bayesian about this and say like, oh yeah, well, based on previous experiences, based on updating priors and a relational observer dependence, we're going to get some changes over time in the predictability of something, but we're going to be able to make some predictions. So what I would say is it's because the indeterminate flows have folded up very tightly into regularly iterating fields that you get the possibility of prediction. But importantly, you also always get this entropy and indeterminacy leaking out of whatever formula you plug in. You're going to get the limits of probability. Now, we don't have to go too far into the limits of philosophical problems and limits of probability, but every probability assumes or picks, at least tentatively, depending on your probability theory preference, picks a field, a range of possible states, or has recorded, if you're a frequentist, it's just you've recorded a series of states that have happened in the past. And then so you call this 100%, and then everything happens within that range of possible states. But the thing is, your 100% is not actually everything that's there. Why? Because you've got indeterminate flows coming in and indeterminate flows coming out, and the entire thing is completely just indeterminate processes that have formed a metastable situation that you've recorded through history or projected, and you're calling 100%. But we don't actually know. All kinds of things could happen. Reality has a really long tail, as they say in probability theory, right? That tail is super long, and it goes out way past 13 decimal points. So I think from a philosophical perspective, we need to at least be honest about what we're dealing with, which is we're dealing with indeterminacy. All our predictions are going to be predictions of metastable states that are relational. So our predictions are, if you needed a quick box to put what I'm saying into, you could say it's a kind of relational probability in which the way that your probability that you're getting is related to the observer. And for instance, just various things like the way that we observe the fact that there's a Planck constant, that's relative to the speed of light, which is relative to our capacity to measure the speed of light. It's a relative measurement. There's nothing absolute about the Planck constant. It's a relational measure. And every time we go to measure, especially things at that scale or very small scales, we're always intervening in the process. And that intervention makes any objective probability theory impossible because of observer dependence. Mm-hmm. Anyway, sorry, I'm gonna stop there. There's more to say about probability theory and the notion of randomness and determinism, both of which I see indeterminacy as an alternative to randomness and determinacy and probability. Mm-hmm. So I'm not saying the world is deterministic. I'm not saying it's random, and I'm not saying it's genuinely probabilistic. I'm saying probabilities are relational epistemologies that we come up with that have not nothing to do with, but they are, I don't know, they're not absolute. They're not genuine objective descriptions of reality like, oh, this is just the statistical likelihood of an electron being here. Well, no, it's related to your observations. It's related to the way you've intervened. It's related to the past history of observations and the initial measurements of the system and the final measurement of the system. Like it depends how you define, like, oh, we're going to start here. Well, if you start here, you got a starting point, but you just chose that. I mean, there's no way to figure out where to start with an electron. Sorry, I said I was going to stop.
Okay, thank you.
Yeah.
Thank you very much.
Very, very nice. So I have some remarks, but later I will. because we have two hands there. So Rodrigo and afterwards Alejandra. So.
Okay. Hi, Thomas. Thank you very much for your talk. I have two questions. First, regarding movement patterns. What about chaotic movements, where there are no patterns, such as the Brownian motion or the climate system, for example? And also, what about fractal motion?
Yes,
such as
yes. Okay,
no,
these
or
are
fungi.
Yeah.
I don't know.
No, this is great. No, these are perfect interrelated questions. Thank you so much for asking, because I didn't talk about them and I thought, oh, I really should have talked about those and I never got to it. No, this is great. Okay, I need the whiteboard again real quick. Oh yeah, oh, one more, okay.
One more. Somehow, I think you complicate the ontology further by adding the idea of a network or a structure of relations. So how can we know if that actually exists? Structures, I think. I think it is easier to give objects their properties of movement or interacting with each other, and thus see them as creating or participating in a structure. Why you what do you want? Why you extend the ontology with structures or network? I don't know.
Can you say it again? I'm not totally sure I understand the third question.
Why? I think you complicate more the ontology with adding network or structures of relation, object relations. So the question is how we can know, how can we know if a structure or a network actually exists?
Right. Yeah. Okay. I'm going to think about that while I answer these other two questions, because I think it's related. It's a related issue. So your first question was about Brownian motion, which is technically a type of fractal motion, but unpredictable motions. So that's the thing, is all these patterns, maybe I presented these in the wrong order. Maybe I should have talked about flows, folds, and fields first, but all these patterns of motion, the centripetal, centrifugal, tensional, and elastic, these are all made of indeterminate motions. But you're right, we can find, these are emerging patterns from indeterminate motions. So movement is fundamentally indeterminate, but then it can fold and organize into relatively metastable states, which then we can classify after the fact. So to me, unpredictable movement, and for me the starting point there is Lucretius's idea of the swerve. He says in the Latin, he says it's incerto tempore, incertisque locis. So it's indeterminate. That's when the swerve happens. He says matter swerves in an indeterminate time in an indeterminate place, and that is the bottom line for him. We never get a deterministic account. We only get this kind of indeterminacy, but the indeterminate movements end up generating patterns, and some of those patterns are these the four that I've said. Others we could call fractal patterns, and the fractal patterns are related. Indeed, they are fractal patterns like Brownian and others. Fractal patterns are actually what all of these the four patterns that I just drew. That's what is going on. All of those together form a larger fractal pattern, or in other words, the fractal distribution is it has the sub patterns of these others. And let me just draw a diagram to like make this kind of spell this out. When we're talking about, so just the universe is starting at a high concentration of energy and it's going to a lower one. That's just what's going on as far as we can observe anywhere and everywhere. We have a starting point. So we could talk about this in terms of the cosmos or really anything, but let's just talk about it at the cosmic level and assume also that that's going on elsewhere. you have some, I mean, what we call the Big Bang, whatever we want to call this, but we have some a high indeterminate fluctuation of energy at the beginning, relative beginning. That energy came from somewhere. One idea is that it was a centripetal contraction of energy from a previous universe or a previous state, but that energy had to be contracted somehow. Unless we just want to magically assume it was automatically contracted into a highly dense state and then exploded. But the idea, I mean, we could also just think about a way a tree grows too. It has roots that suck water in and nutrients. And then in terms of the Big Bang or a tree, we have this first kind of, once it gets to a point of accumulation, only once you have a point of accumulation can you get a centrifugal expansion. Can it pour outward in the form of a tree, outward in the form of a universe, but to produce entropy. So energy explodes outward in all directions. This is a centrifugal movement, even if it's not, I know the universe doesn't have a center, but like the basic idea is that you've contracted into accumulation and then it explodes outward from some concentration of some kind. Obviously, we're dealing with a more complicated thing in the case of the universe. I should have stuck with the tree example because we're dealing with the origins of space and time, and trees are already in space and time, so that's easier. In any case, you have something like a first explosion outward, and then from outward it branches into several other smaller branches. Here we could say, in the of a tree, this is obvious. You have the tap, the trunk of the tree, the branches of the tree, and then you have, sorry, this is coming back to the patterns of motion, I promise. And then you have smaller, leaves and veins of the tree. Now, each of these stages maps onto the patterns of motion that I described previously. A centripetal contraction, a centrifugal expansion outward, a tensional relation here between a bunch of diverse branches, either trees or we're talking about the distribution of dark matter and galaxies. They all branch out, but they hold together in a very specific pattern in every single case. And then the final one is elastic. Those elastic ones are often the smallest, the most numerous, and the distribution, sorry, I mean, I don't know how well you all are thinking about the mathematics of like fractal distributions, but it's roughly what is called like a 1F distribution, 1 over frequency, where as the frequency of something increases, the amplitude decreases, and you have a distribution of the distribution of dark matter in the universe is fractal. I mean, the patterns of it, when you look at the distribution, you have the kind of spider webby tendrils of distribution of matter. It follows a similar fractal pattern. Why? Because the birth and process of the whole universe, what the universe is doing is this. That is why the trees have that fractal distribution, that branching and iteration, but it's because at each stage you're dealing with a contraction of energy, an expansion of energy, and then a branching of that energy into smaller and smaller rivulets. So, if we want to talk about watersheds, the way that water deltas branch out, we talk about tree branching, we talk about neurons in the brain, the distribution of dark matter. At every stage, we're looking at these 4 patterns of motion. That's like the breakdown of the larger fractal distribution of the universe. The third question, of why add these patterns onto the core ontology of flow, fold, and field. I would say that you're right. I'm not like, maybe you could go other ways. Maybe you could probably take what I've said and be like, yeah, I like the flow and the fold and the field, but I'm not sure about these patterns. That's totally fine, especially if you haven't read my works but I've really tried to make a case that these patterns are historically useful. Why do I need them? Because it's not just that things move. Things move because in a very specific way in this universe, they move by entropy. And entropy, one of the fastest ways, again, it's not totally universal, but one of the absolutely most optimal ways to dissipate energy is fractally. fractals are one of the best ways to dissipate energy, and that is why human culture, animal populations, particles, all distribute themselves in these fractal patterns. Again, I can't go on for every single example at every single scale of reality. I'm just going to say this and refer to the books. But that in every case, these are the patterns that are going on. So how do we know that they're real? Because we're here and we're real. I mean, if everything is in movement, we should expect that there'd be some patterns in a particular universe, which we're in. We're in a particular universe. And one of the key features of this universe is that everything is spreading out. So if that's true, then we're going to get the optimal spreading patterns. We're going to see them a lot. Spiral galaxies. We're going to get branching galaxy clusters like Laniakea. You can see in the Laniakea galaxy cluster, it looks just like a giant tree. Galaxies spread out, and then each of those galaxies spirals around because they're all diffusing energy, most of them around giant supermassive black holes. Because just like when you flush a toilet, it's the same idea, you know, the water drains spontaneously in a funnel, but that's going on at every scale of the universe. So you're right, it's an addition to the story, but for me, this is actually where we get something like a predictive model that can help understand really large and really small patterns of emergence. We can look at things and understand and predict with some degree of likelihood what they're going to do. They're going to spread out, and they're going to spread out in these patterns. They're not just going to spread out randomly because, yeah, there's no randomness. Anyway, sorry, I've taken too long here to answer the questions, but I appreciate, especially that third one. It's made me think harder. Thank you.
Yeah. So Alejandra.
Presentation, it's been very inspiring. I try to think your concepts through my practice. I make live noise performances, so it's a kind of music that doesn't have a melody or beats, and it's a process really of trying to make borders, like emergent borders. And so when you spoke about motion patterns, I could realize that all of them are contained in the live noise performance, but mainly the elastic pattern. But then again, you mentioned cycling, and so I wonder what you think of time and rhythm within your framework, especially because I see that all of these motion patterns happen simultaneously sometimes, and but also they are time dependent. So what's your idea of rhythm and time?
Yeah, thanks. Yeah, those are great questions. And yeah, a really interesting one about noise music. Yeah, I listen to a lot of noise music and field recordings and stuff, so I'm familiar. But I would say that you're right. They're not necessarily like the four patterns aren't necessarily like developmental in any like teleological sense. But you're right, they happen together all the time to varying degrees. Sometimes one of those patterns will become dominant and then it will fade away. And I mean, this is the case in human culture, society. It's the case in the arts. It's the case in the sciences, that these patterns come and go, but they're all always there to some degree. But sometimes one really takes the foreground and displays that pattern. And it's sometimes very interesting to see the alternation, a quick alternation of all the patterns to see that they're all going on. But time and time, so what for me, what time is it's just entropy. I wouldn't say that I don't have any like metaphysical idea of time, like it's some kind of line or chronology, like everything's here all the time. You know, I mean, you're always dealing with a distribution of energy that's always going from more concentrated to less concentrated. And time is just a name that humans have given when that happens. We just call that time. But you're right, each of these stages of motion, they are time dependent. And in this case, that means entropy dependent. For me, energetically dependent on one another, that one comes out of the other, because every later stage requires energy from the previous in order to dissipate it, and it's always trying to spread it out more and more and more and more. And I think you're right that the elastic one is a much closer characterization of noise than the other ones, because the elasticity can really rapidly, it's going in all these different directions at once, and it opens up, it is a maximum release of entropy. I mean, you can think about things that are on those fringes of like leaves. I mean, what moves more, the tree trunk, or the branch, or the leaves? The leaves always move more. They're out there shimmering. And when you think about music, I mean, music can have, it can be more or less diverse and shifting. It can have more rhythms or less rhythms, but noise, it really pushes those very limits of how energy and all the different ways energy can be released. So it challenges your brain and pushes it over the edge of of possibility, but pushes and makes your brain more entropic even to listen to it. It pushes it to the limits. But what I would also say about some of those limits is within noise, I think some people think about noise, I mean, in all levels, not just noise music, but all levels, they think about it as like random. And I'm almost certain that you don't think noise is random. And I completely agree, but that is people's first expression. They look at a Jackson Pollock painting, they listen to, some noise or drone, and they're like, this is just random. This is like randomness, and it's unpleasant, and I have no interest in it. And the thing is, they're not realizing that it's not random, but their first impulse is that it's so much going on that they can't tap into it because they haven't had the patience to tune in. But if you tune into a Jackson Pollock painting, you will see that it is absolutely complex and rich and filled with fractal patterns. And it's the same, my hunch would be with noise music, although I'm waiting for the study to show this, because most music has a fractal distribution of frequencies, but noise music has so many frequencies. I'm almost certainly convinced that noise, not all of it, but much of it would have a fractal distribution of frequencies. I don't know if anybody's tried to do that, but it'd be an awesome experiment to check, you could check the 1F distribution of frequencies in various pieces of noise music. And my hunch is that you'd find a fractal pattern in that. And that would account in some ways for the appeal. I think there is both an appeal and sometimes a difficulty of listening to noise music, a challenge, but also an appeal that draws you into it. Even if you're looking for the pattern, like the pattern is just enough to pull you in and then take it away from you at the last minute. But that's why nature is beautiful. That's why so many things are interesting, is because, like a tree, every single leaf is different. You get the general pattern, but if you look closer, you see that it's actually all very different. No leaf is the same. All the veins are distributed differently. They're all deformed in their own way. And that throws you off, but it throws you off in just a way that like keeps you coming back to keep looking at it endlessly. Anyway, yeah, I don't know. Do you know of any studies thinking about the practicality of noise music? Okay.
No. Thank you, Thomas.
Yeah, thanks. Great question.
So, David?
Yeah. First of all, Thomas, thanks for your talk. It's been very enlightening. I'm going to make two different questions about migration. So my interest is political. You have talked about 4 different patterns of movement. As you have presented them, it seems that each of them was directly or maybe indirectly related to a specific historical period. So my question is, I was wondering if these 4 patterns can be used to eliminate more recent migratory or refugee movements, because I was thinking, for example, in Jewish diaspora. And it seems like in the Second World War, maybe it's a centrifugal movement from the center to the periphery to a very different locations across Europe or North America. And maybe when the State of Israel was created after the Second World War, it's a centripetal movement from the periphery to the center. No? And that was my question is if you have made specific studies about more recent historical periods, like in contemporary periods or other.
Yeah, that's a great question.
And sorry. And my second question is, you have talked about migrants in general, but I suppose that since you are interested in migration, you distinguish between economic migrants and refugees, I suppose. And I was wondering if are there any differences between in these four different patterns of movement between economic migrants and refugees. Thanks.
Yeah. Okay. Yeah, that's a great question too. The first one is so the Figure of the Migrant book and the Border book, at the very end, there's a section on contemporary migration. I mean, there's so much contemporary migration, like I can't possibly keep up with every single study, but I would say that I will tell you the main idea there. The main idea is that all the historical phases, each time each one of those patterns in history emerges, it and becomes dominant, it continues with the rest. So by the time you get to the present moment, you're dealing with all of the patterns of motion, and you get a mixture of them. So every case study we would look at for a diaspora or a refugee movement, every particular case is going to be a mixture of these four patterns of not just of social motion, which is to say the ways in which because people have been always moving, will keep moving forever. That human movement is just a thing about the world and humans. So to me, the starting point is that humans move around, and then through history, they get called different names. Sometimes they get called barbarians. Sometimes they get called vagabonds. Sometimes, they get called refugees. There's all these nomenclatures, and those vary through history of how people call them, and also how societies sculpt a migratory landscape, if you will, allowing some people in, ushering some people out. And that really is related to the form of society that they are. Is it a state society? And the mixture of those things, right? Is it an ancient empire? Is it a modern nation state? Is it a modern capitalist nation state, right? I mean, which arguably those things go really closely hand in hand. But the relationship of economy and capitalism and the nation state shape the way that migrants are understood historically. So the idea of economic migrant, I mean, that kind of only makes sense, in a certain historical context and geographical context to think about migration in that way. Whereas if you're talking about prehistory, that doesn't make any sense to think about it in that way. Or in the ancient world, economic migrant. No, I mean, there's slaves. You can call people going, but people wouldn't have used that term, economic migrant. Anyway, so my point is there's a whole nomenclature to think about, but each of those nomenclatures comes along with a historical pattern. So for instance, there's different ways. Let me give you two different perspectives, because these are the main competing ones right now. I would say if we want to talk about contemporary migration, there's two really big competing stories that are at odds with each other, but that work hand in hand. They seem like ideologically they're at odds, but kinetically speaking, they're very much fit together like a glove, One is the narrative which is a kind of a centrifugal narrative of the nation state. So this is the hardcore xenophobic right-wing nationalist story, is this place for our people, everyone else no. This is the nation state defined by this language, defined by these people, by this color, by this everything, and everyone else is the attempt to push them out. I'm just thinking here, we could talk about all kinds of variations and degrees and contexts. I'm thinking of the United States only because it's my context, but that's what's going on here. There's that movement of the right wing is to kick out, to remove all undocumented migrants from the country, all 11 million of them. Just kick them out. That's the solution. Okay, it's ridiculous. It's never going to happen. But here's the other thing. If it actually did happen, it would totally destroy the economy. That's why it seems at odds. You're like, well, that's just kind of racist, to do that. Okay, that's going on. But that form of American racism against migrants, it comes from a historically centrifugal, that's originally an ancient idea that there is a race for a place with a language. That's Aristotle. I mean, that is that, and everyone else is a barbarian. And that is quite literally the rhetoric used around migrants in the United States from, Latin and South America and Mexico, is that they're barbarians. They don't speak the language, all this stuff, it's all back to all this stuff comes from the ancient world. But the other competing one is the capitalist narrative, which relies on economics, right? It relies on migration. It is fueled by undocumented migrants who are ultra exploitable because they don't have documentation. So they can be underpaid, overworked, completely abused, and have no political power whatsoever. That is really the ideal kind of worker for capitalism. So they really want that. But you see that in America, these are the two things that on the surface of it sound like capitalists want undocumented migrants. Right-wing nationalists from the ancient period don't want migrants. Now, the ideal situation is that, like what's happening now, what's the reality and how they work together is that it's racism and xenophobia and criminalization that make possible the undocumented person that can be maximally exploited by the capitalists. So the capitalists benefit, they feed off of that ancient model of racism and barbarism or whatever. They feed on that and make money and profit off of it. But they're never going to say it outright. You know, that's not what they're going to say. They're going to say, we follow the law and we are in favor of the law. And, you know, whenever they get a chance, they'll try it, like Apple or Google. You know, when there was a ban on Muslims, Apple and Google were like, no, it's a human right to migrate. It's like, you're just upset because the countries where you got your workers were banned. Like, this is obviously self-interested, but they say it in the name of like liberal, progressive, inclusion. But really it is all about, exploiting migrant workers. That capitalists are in favor of it, but they're also in favor of criminalizing them because criminalized migrants are easier and better to exploit than non-criminalized. If everybody had status in the United States, that would be a blow to capitalists everywhere, because they would say, oh, we can't hyper exploit these people because now we have to like pay them minimum wage and give them benefits, and their taxes will actually go back to them instead of just being stolen by the government. Both the state and capitalism have nothing to benefit by giving migrant workers status in the United States. Okay, well, there's a million examples and case studies we could look at. My point is just that in the contemporary period, you always get this weird mixture, and the mixtures are different. It's not all like the United States. The mixtures of ancient, modern, and medieval, and even prehistoric, like they all, they work, they're all mixing together, and some are very powerful and some are very weak. Arguably, the kind of Neolithic or more prehistoric forms of migration where you just go from territory to territory, that is very weak right now. There's not a lot of that. It's mostly dominated by states who control those borders and capitalists who profit from the every single aspect of it. Don't get me started unless you want to get me started.
Thanks.
Did that answer the second question too? I'm forgetting.
Yeah, in a related way. Yeah. Thanks a lot.
Okay. Yeah, no, it's a good question.
Well, okay. I don't know if we have some questions from YouTube. No? Well, so I have a comment only because I greatly appreciate your talk. And this is connected with the question by Juan, but Juan is not there, I think. Well, because about prediction, indeed, prediction is connected with the idea that one can guess, say, what rules motion. And the law of motion, say, of the movement. And indeed, I think that one has to think about some of the, say, the categories you introduced, because you have flows and measurement. We need to perform measurement to understand the motion, so the motion of other flows. And so one construct, say, a compendium of events, events being, say, the intersection of flows. And so we get an idea about what is ruling the motion, but up to those events. And then the problem of state as say what rules the event, the motion, well, one cannot determine the state, that is what is ruling the motion. When one starts, say, pursuing the state by means of measurement. So indeed, for me, the state is not given by one measurement, but by a family of measurement, or say is a whole sequence or family of measurements. So the only thing one can do is to have an idea of a prediction, but a prediction in terms of the history. So it's a historical problem. So the prediction, well, in the theory of processes in mathematics, in the theory that we started working on in the 70s, there was, in the general theory of processes, there was the introduction of the notion, say, the representation of histories, and predictability. And so we classified events, say, or processes as predictable or non-predictable. And so in the theory of open system dynamics, predictable processes are those that we can really manage, transform, and so we know those processes. And unpredictable processes are connected with the, say, the environment, and noise is connected with the environment. And so, well, I think that one has to work on predictability or prediction of a theory in terms of history. So
yeah, I'm with you on the idea of thinking about it historically, but I would also add that, and correct me, maybe I'm misunderstanding how you're saying it, but I would not frame the problem in terms of there is or is not a predictable pattern, or that there is a predictable pattern, but it's negatively influenced by noise, and so it distorts the pattern. I think that the pattern emerges from the noise. Like, there is only noise. And by noise, I just mean the fluctuations of energy. But I mean, at every level, there's only noise. Yeah. And I mean, thinking about it at a neurological level too. We're dealing with brain, 99% of brain activity is what neuroscientists call spontaneous fluctuations. They don't really have a sense of what these fluctuations do. But every now and then, that 1%, they can get a functional spike, and then they can average out all the rest of the noise. But to me, this is a good example, but it's across every field. It's not just neuroscience, but background noise everywhere. That is it's those noises that build up the patterns. It's only relative. It's out of the noise that the patterns emerge. So like distinguishing between noise and pattern, I think it might be too far. I think we're really just dealing with noise pattern. There's patterns of noise, but like when they're patterns, we don't call them noise. We just say, oh, I hear a bird chirping, and like that, there's a pattern to that or something. But like, yeah, but what actually is that pattern? I mean, it's mixed with everything around that thing too. It's the whole acoustics of the area where the bird is singing. It's all of these other influences. But what goes on is our brain filters out a lot of that and then identifies birdsong as being distinct from all the other sounds that we're hearing, including our own breathing and our own heartbeats. And like, there's a lot of filtering going on. But I mean, if you get at noise in its raw state, you see that it's all unfiltered, that we add the filters. So Yeah, I mean, I think you're always dealing with noise built up into patterns and rhythms and layers. And then when you go to make a measurement, you're selecting some, yeah, like you said, you select some group, and importantly, you track the history. Like, I agree with that, is you're making a measure, it's like you don't just do one measure, it's that you have to constantly keep measuring, or that you can, and that each one of those measures is you're cutting a slice out of the noise and calling it, that or something.
Yes, no, I agree with that. That is, noise is a representation, say, of all other flows you cannot transform directly. They are there, all those flows. And well, I am thinking to John Cage, 4:33. Well, so they are there. That's why I think a way to understand that relation is through the open system dynamic theory, where you put the noise, say, as the representation of the environment, that you only that you can only say see indirectly, or you measure that indirectly. For instance, in Brownian motion, you have the pollen in suspension there on the liquid. You cannot see the molecules, say, pushing the pollen, but you can put a thermometer to measure the dissipation of energy. So
right.
indirectly, you measure the noise.
Yeah, I mean, well, exactly. And the parallel is in quantum mechanics. Like, there's no direct measurement of quantum indeterminacy. There's only indirect measurements, or like
Yes.
vacuum fluctuations. No, you can't directly measure. That's like way too small of a level. You're looking at, you can just indirectly see that based on its effects on, subatomic particles. You can see that there is energy there. It is doing something. We just don't know what it's doing, and we can't measure it directly. Yeah. And I think that's a really important aspect of measurement and the generation of objects. It's important to remember, and this is like a key idea. And maybe if anybody remembers anything from this whole talk, this is like the fundamental orientation that Orlando is saying, is like that objects are processes, and they're like, just to go back to this history idea, like you have to keep doing it. It's not like there's just objects out in the world. It's that, like, if there's objects, either humans or nature have to keep doing something to keep maintaining that object, or else it's not there anymore, And every one of those maintenances, it's like, we're not just counting something out in the world, we have to keep counting it, like, is it still there? Yes, it's still there. How do you know it's still there? Well, we put it in a box, like we recorded it and we know it's there, but we have to keep checking. And that's, I mean, history, not just in the kind of formal sense of mathematical histories, but in the material sense of histories, of like, it has to be like, every object has to be like made and remade over and over and over again. You can't just measure something once. Every time. And like the whole premise of like reproducibility and experimentation, somebody else should be able to reproduce it, or else it doesn't exist. You just saw it once and now no one else can find it again. Yeah. Maybe it's not real. Maybe it was a fluke. Maybe it was other things. The reproducibility of the object is crucial. And I think sometimes people in logic or mathematics think that what they're doing is like pure forms, and they're just recording, objective states of things. It's like, no, even mathematics, when you write it on your computer or with a pencil or draw it, you're making it. Like, there's a constructive dimension to mathematics that includes the maker of it. It only exists I mean, whatever, this is category theory, but I think there's a truth to that part of category theory, which my version of it might be slightly more radical, but, is just that you got to select the axioms you want, like there's just no default axioms. You make the axioms, you make the topos, right? You make the world, and then you fill it with things. But that world's not there unless you make it and fill it with stuff. And that's the way in which the object has to be iterated and made. But the problem with that is never gets iterated exactly the same way twice. And so you never have exact reproducibility. And hence, Rolando, your point about histories is you're never getting the same one twice. Even when you do the histories, you might be like, oh, it's the same, it's the same, it's the same. We'll go back and look closely. You'll see every leaf is different. Every measurement was slightly different. Mm-hmm. Even when you called it the same thing, it might have worked differently, in part because of the relations that it was in part because of the way that you did it, in part because of the history that it was embedded in. So, I mean, it's a much messier process. And so, you know, every now and then, if you don't think about these kinds of things, this framework that we're talking about, if you don't think about this stuff, you might end up with problems that are very surprising and random later on. You know, like, oh, who knew that could happen? It's like, well, of course, that's a likelihood that might have easily happened. You just pretended like it wasn't always going to be the same. So then when you found that it was different, you were shocked. And like so many scientific discoveries happen in that way where it's like, oh, and surprise, we had no idea. It's like, well, you didn't have any idea because you assumed that that wouldn't happen because you made the measurement and you made it twice and you thought it was going to keep being the same. But the world's just not the same, nor are you. So we should expect but the unexpected, you know, we should expect surprise. We should expect indeterminacy. We should expect noise where we didn't expect to find it. And that should be the starting point, is to expect turbulence and unpredictability instead of, you know, being surprised when it happens and a failure of our system to record it or something. Yeah, it's a different way of thinking about the whole of many of these projects, so the orientation.
Yeah.
Sorry, but
well, Thomas, I know that you have another talk now at 11 your time. Yeah. So,
yes. But well, I have time for one more. If Rodrigo had a question, I can respond.
Yes, but
I have a few minutes.
But Pablo Marquet wrote a message for you there on the chat. I will read it. Thank you, Thomas, for your talk. I have to leave. Interesting, but I think that several of the ideas you present need physical and mathematical justification, which is the challenge we all face. Cycling, for example, is well justified in the work of Onsager and was further elaborated by Morowitz, but beyond that, we need justification.
I will only say it's in the book. Onsager, Morowitz are cited in my book. Yeah. I'm with you. Like I said, I'm making some very big moves to show the big picture, but all of the justifications, you know, I've tried to cite all of those in the book, and give lots of examples physically and mathematically of how what I'm saying is consistent. But I just can't reproduce all that now. It would take hours. But Rodrigo, did you have something?
No, just a comment. In spite of randomness, I think that we have constants in the universe or not. For example, I don't know, magnetic permeability of vacuum, the universal gravitational constant, the Planck's constant, for example. I don't know. We have constants or not?
Okay, good question. It's been a couple of years since I got into this question about the universal constancy of light. My memory, I'm going to say no, but I'm not sure if I'm going to fully remember the whole rationale behind it, but I'm going to do my best. I don't think that there are constants in the universe. A couple things. One, universe is pretty big and we know about 1/200th of it. So I'm not going to go as far as to say that we're definitely sure about the constants of the universe. Number two, the universe itself is an emergent metastable state. Whatever we have now emerged from something that wasn't there previously. So the speed of light as a constant. The speed of light is something that is a feature of our universe that emerged historically. And there's no determinacy. It didn't have to be that way, but it's relatively stable according to our measurements. And that's the third point, according to our measurements. The constants we have are relative to our capacity to measure them. I don't think that they're absolutely objective. I think that they're relative to the ways in which we can measure. And the Planck constant is a good example of a constant below which we, not just that, like, okay, experimentally, we're nowhere near being able to measure something like that. It's a mathematical idea based on other constants. But the problem is that it's not like, is it really, like, does nature say like, oh, below this, who knows? Like, nature doesn't say that. There's stuff going on. We just don't know what it is because we're using the constants that we have, namely the speed of light, in order to try to deduce what might be going on. So it's not like there's nothing below the Planck constant. It's that there is energy, but it's so indeterminate. And when we go to measure energy, again, theoretically, right? If we went to go measure a unit of energy or a length or something below the Planck scale, we end up getting basically really nonsense, contradictory types of information from our equations. The equations don't make sense. It appears that things can both be and not be at the same time, and that they are both longer and shorter than the Planck constant. You get all these errors in the measurement of energies that are so high that they no longer fit. Now, does that mean that like there are not energies at certain levels, or does it just mean that relative to our capacities to measure them, they appear to us to be, they don't make sense? Again, there's more details I'm not fully remembering about this particular argument. And I have an article that I read recently that gave me, like, written by a physicist who was sympathetic to the idea that the constants are relational, especially given quantum indeterminacy, because that might be another thing to consider, is that if there is genuine quantum indeterminacy, then I'm not sure we can talk about a perfect constants. No, okay, constant enough. Yeah, constant enough for us to do some stuff, fine. But if we're going to be really ontological about this, I'm not sure if we could say that there's any constants if everything is moving and quantum fluctuations are fundamental. Again, those are ifs, but if they're true, and as far as we know that is the case experimentally, then I don't think we can ever have any absolute constants. But they could be constant enough to get us to the moon, you know, in terms of universal gravitation. Like, yeah, we can launch a satellite, you know, we got our iPhones, it's enough. But it's not exactly right. It's there, and the universe is not always the same. The speed of light is different each time, but it's happening differently at such a level that's negligible to our goals. Okay, but I think I do need to go now, Rolando. Yeah, but I really appreciated everybody's questions. It's been really great. It's great to engage with you all. It's really nice to talk to interdisciplinary people engaged in the sciences and arts.
So, well, thank you again. Thank you very much. And I think we will keep in contact, Thomas.
Please do. Yeah. Anybody send me things that you think I should read, and any follow-up questions that you have.
So.
Yeah. Bueno.
Okay, we'll be in touch. Thank you, everyone.
Thank you. Bye all.
Bye.
Bueno.